This apple falls to the ground, but this apple falls much faster. Why is that? Well, it has to do with mass. This apple has more mass than that one, so it falls faster. But wait, that isn't right. Isn't it true that all objects fall at the same rate regardless of their mass? Yes, that's true. That's how gravity works. So if we drop two balls of different masses, they should hit the ground at the same time. In fact, they do. But if we drop them from a great enough height, air resistance becomes a factor, and the heavier ball will win out and hit the ground first. If we could eliminate air resistance, all objects would indeed fall at the same rate regardless of mass. And we can verify that by dropping things from low enough heights where air resistance does not play a big role. So what's going on here? Why does the heavier apple fall faster? It's because the heavier apple has a stronger gravitational pull. Every object in the universe attracts every other object with a force we call gravity. The more massive an object, the more gravitational pull it has. So when the apple falls, it pulls itself towards the earth, but the earth also pulls the apple towards it. And since this apple is heavier, it has more mass, which means it has a stronger gravitational pull. So it's not quite accurate to say that the earth is pulling the apple down. It's more accurate to say that the apple and the earth are pulling each other together. And because this apple is heavier, it pulls the earth towards it just as the earth is pulling it towards itself. Since the apple is also attached to the earth by a strong gravitational pull, the apple pulls the earth slightly closer to it. Then, as the apple gets closer, the earth's gravitational pull on it gets stronger, which makes it speed up. Since the lighter apple doesn't have as strong a gravitational pull, it doesn't speed up as much as the heavier apple. Of course, the difference in speed between two apples isn't something you're likely to notice, but it is still there. This is why the apple with more mass falls faster. Now, if we were to take the two apples and attach them together, so they become one apple with twice the mass, then that apple would fall even faster than the heavier individual apple because it now has twice the gravitational pull. And if we attached many apples together, making one large apple, then that apple would fall even faster. Or if we took the flour and the sugar and mixed them together, making one large clump, then that clump would fall faster than either the flour or the sugar on its own. And if we took Earth's mass and somehow managed to shrink it down to the size of an apple, then that apple-sized Earth would have twice the gravitational pull of a regular-sized Earth. So things would fall twice as fast on it. Of course, there's no way we could ever actually do that without destroying the universe or something, but it's still a fun thought experiment. So that explains why the heavier apple falls faster, but it doesn't explain why anything falls at all. Why do apples fall towards the earth? Why don't they fly off into space? Well, that has to do with Newton. One day he was sitting outside and he saw an apple fall from a tree. He wondered, why did the apple fall straight down? Why didn't it go sideways or upwards? He considered the possibility that maybe the apple was attracted to the center of the earth, so it fell straight down towards the core. But if that were the case, then when the apple got to the core, it would keep going down through the center of the earth and out the other side and eventually fly off into space. But that's not what happens. So he reasoned that maybe the apple was attracted to every part of the earth equally, so it fell straight down towards the center of mass of the earth, which just so happens to be in the middle. But that raised another question. Why did the apple fall towards the earth at all? Why didn't it just float away? Well, Newton realized that there had to be some kind of force bringing the apple back down towards the earth. He called this force gravity. He concluded that all matter attracts all other matter with a force that depends on the masses of the objects and the distance between them. He discovered that if you double the mass of an object, you double its gravitational pull. And he also found that if you double the distance between two objects, you only increase the gravitational pull by a factor of 4. So if you double the distance, it's like you cut the gravitational pull in half. So doubling the distance between two apples would make the gravitational pull between them only 1/4 as strong. So from these observations, Newton came up with a formula for calculating the gravitational pull between two objects. And this formula tells us that the force of gravity between two objects depends on the product of their masses divided by the square of the distance between them. Now, according to this formula, the gravitational pull between the apple and the Earth should depend on the mass of the Earth and the mass of the apple, but it shouldn't depend on the distance between the apple and the surface of the Earth. This means that if you doubled the radius of the Earth so you made it bigger, but kept the mass the same, then the gravitational pull on the surface of the Earth would be 4 times weaker, because doubling the distance makes the gravitational pull 4 times weaker. And since the distance between the apple and the surface of the Earth is now twice as great, the gravitational pull is 2 times weaker. So if you made the Earth twice as big, the gravitational pull on the surface would be twice as weak. But if you made the Earth 4 times bigger, the gravitational pull on the surface would be twice as weak. Twice as weak as twice as weak, which is 4 times weaker. Now, this may sound counterintuitive, but it makes sense if you think about it. If the Earth were bigger, the apple would be farther away from most of the Earth's mass, so the gravitational pull would be weaker. And since the Earth's mass would be spread out over a larger volume, the density would be lower, which means there's less mass per unit volume, so the gravitational pull would be weaker. But there's another way to look at it. You see, if you increase the size of the Earth while keeping the mass the same, then you increase the mass of any object on the surface of the Earth by a factor of 8. This is because if you increase the radius of the Earth by a factor of 2, then the volume increases by a factor of 8. So if you keep the density the same, then the mass must also increase by a factor of 8. So if the Earth were twice as big, everything on its surface would have 8 times the mass. So the apple would have 8 times the mass, which means it would have 8 times the gravitational pull, so it would pull the Earth towards it 8 times as hard. And since the Earth is also pulling the apple towards it with a force that depends on the mass of the Earth and the mass of the apple, the gravitational pull between the apple and the Earth would be 8 times stronger. So if the Earth were twice as big, the gravitational pull on the surface would be 8 times stronger. And if the Earth were 3 times bigger, then the gravitational pull on the surface would be 9 times stronger, because 3 cubed is 27. So it seems like the size of the Earth should affect the strength of the gravitational pull. But remember, the size of the Earth isn't really relevant. What matters is the mass of the Earth. That's why Newton's formula says that the gravitational pull between the apple and the Earth depends on the mass of the Earth, not the size of the Earth. In fact, if you wanted to calculate the gravitational pull of a planet that wasn't a perfect sphere, then Newton's formula wouldn't work because you'd have to take into account all of the different distances between the apple and all of the different parts of the planet. And since Newton didn't know calculus, he couldn't figure out how to do that. So instead, he used a shortcut. He assumed that the planet was a perfect sphere and that its mass was evenly distributed throughout its volume. This allowed him to treat the planet as if all of its mass were concentrated at its center, and then he could easily calculate the distance between the apple and the center of the planet, which allowed him to use his formula. But if you wanted to calculate the gravitational pull of a lumpy potato, then you'd have to add up the gravitational pull from every little piece of the potato. And that requires calculus. But Newton didn't know calculus. Calculus wasn't invented until about 300 years before Newton's time, so he couldn't have used it to calculate the gravitational pull of a lumpy potato. Instead, he used calculus to come up with a formula that worked for spherical objects. But I'm getting a bit off topic. The point is that according to Newton's formula, the gravitational pull between two objects depends on the mass of the two objects and the distance between them. But that still doesn't tell us why things fall towards the Earth at all. Why don't they just float away into space? Well, Albert Einstein figured that out. He realized that there must be some kind of energy associated with being in a gravitational field. He called this energy potential energy. So if you lift an object up, increasing its potential energy, then let go, the object will fall back down, because the potential energy will turn into kinetic energy. So it turns out that the reason things fall towards the Earth is because they have potential energy. And the reason they don't float away into space is because they're not getting any higher. So if you put an apple in orbit around the Earth, then it won't fall to the Earth or float away into space. It'll just stay in orbit. That's because the apple is high enough above the surface of the Earth to have significant orbital velocity. This means it's not getting any closer to the Earth, so it's not falling. And it's not far enough away to avoid the Earth's gravitational pull entirely, so it's not floating away. It's just in orbit. Okay, thanks, bye.